Welcome to the sixth and final installation of Green Building Research Institute's case study series, Lessons Learned from 99 LEED Projects. I'm Rebecca Joan Brown, and I'll be leading the course discussion today. Lessons Learned from 99 LEED Projects is a six-part series focusing on how projects that were successful in implementing LEED concepts did so effectively. In this series, we look at 99 LEED Gold and Platinum certified projects to identify what strategies are most effective and earn the most points in the 6 LEED credit categories. We will be discussing some of the most frequently applied strategies, those that are easiest to implement, and some of the interventions that stand out as especially unique or elegant solutions. Today's presentation focuses on water efficiency and water conservation. Today's course will focus on providing an overview of the LEED credits available to projects for water efficiency measures in the 3 largest LEED rating systems, BD&C, ID&C, and O&M. We will look at the requirements for each of the relevant credits and suggest solutions to earn these points that were common in the 99 projects that we evaluated. We will also profile projects that demonstrated exceptional dedication to their water conservation goals and earned some of the highest scores for the water efficiency section. Here's a list of our course objectives for today. The overall goal for the 99 project series is to introduce you to strategies that can help your projects become LEED compliant, as well as to give you an understanding of what successful LEED projects found to be the most useful tactics and most worthwhile credits to pursue. To that end, we've identified 5 course objectives for you to benchmark your successful completion. First, you should be able to describe the credits available to projects in the water efficiency category of the 3 major LEED rating systems. Secondly, you should be able to discuss the intents of the water efficiency credits and identify the credits that are most frequently earned. You'll be able to analyze commonly implemented water efficiency measures and evaluate how well they will work for your future projects, and will be able to describe some of the more exemplary solutions that we discuss. Water efficiency relates directly to overall water conservation. Water has long been a precious resource in certain parts of the world and is becoming an increasingly sensitive issue in the U.S. as development expands and rivers are dammed or diverted to allow for growth and increased agricultural needs. Conserving water prevents the depletion of aquifers, which provide water to about half the population of the U.S. These aquifers naturally operate in a sort of equilibrium, where water is absorbed by vegetation or discharged into water bodies, and is recharged through rainfall and percolation. As these aquifers are depleted through personal and industrial use, many cities and regions are forced to place restrictions on water use, and political battles concerning water rights between states and municipalities are increasingly common. Water that is used for buildings must be treated before it is reintroduced to the water cycle in order to eliminate waste that would be biologically harmful. The water treatment process consumes energy, so reducing the need for water treatment will also result in energy savings. Even after water's been treated to remove waste, it is often reintroduced with other contaminants, and water that is used for agriculture and irrigation is reintroduced without treatment. Water that is reintroduced to rivers, streams, and aquifers often contains harmful components, such as nitrogen, phosphates, bacteria, pharmaceutical residues, and toxic metals. These compromise the natural environment and the habitats that are dependent on those water sources, as well as posing a threat to human health in some cases. The way that water is removed from a site is also important to the environment. Drainage systems that are not carefully planned can lead to the erosion of the landscape and sedimentation in streams. Using more efficient water systems and fixtures in buildings can save projects millions of gallons per year, which reduces costs as well as environmental impacts. Gray water collection involves collecting water from the building and recycling it back through the systems. Gray water may be collected from sinks and kitchen uses. However, black water that has come in contact with toilet waste is considered contaminated and must be excluded from gray water collection. About 50 to 80% of a building's wastewater is gray water, so by reusing this resource, a lot of potable water can be conserved. Building gray water is collected and then reused for tasks that do not require potable water standards. Some filtration may be required, especially if using gray water for irrigation, as some of the particles that are common in wastewater can be harmful to plant life, such as salt or detergents. Some of these contaminants can be mitigated by having building policies in place that specify more eco-friendly cleaning products that can be easily broken down by plants. Treatment of gray water may be done chemically in a storage tank, or water may be discharged to constructed wetlands for biological treatment. Another condition when looking at gray water systems is the need for separate plumbing, which adds significant costs to a construction project. In typical wastewater systems, gray water and black water are collected in the same pipes and discharged together. For a gray water collection system, a separate system would need to be installed in order to discharge water from showers, sinks, and other gray water sources to the treatment system, while black water is discharged to sanitary sewers. As we mentioned before, many local codes require that pipes conveying gray water for interior use be designated by a different color so they will not be used to supply potable functions in later renovations. Many states and local governments have restrictions on how gray water may be used, so be sure to check with local authorities to ensure the building designs comply with local codes. The BD&C case study that we'll discuss is the Sidwell Friends Schools middle school expansion in Washington, D.C. This LEED Platinum project earned all available points in the water efficiency category, as well as an exemplary performance point for water use reduction. The project is situated uphill from Parkland and between two ecologically sensitive watersheds, so controlling the contaminants that leave the site through stormwater was a major project goal. The building installed a green roof and located parking below grade to reduce impervious areas and foster water retention on-site rather than runoff. A constructed wetland on-site treats rainwater as well as building gray water from kitchens and bathroom sinks, which is then reused to flush toilets as well as provide water for the building's cooling tower. The faucets in the building's restrooms are equipped with sensors and have low flow rates to further conserve building water. Through a combination of native plants and the use of stormwater and gray water, the building is able to use no potable water for outdoor use, and the interior conservation systems and water reuse allowed the project to reduce indoor potable consumption by 90%. The green roof and the water treatment system are integrated as a part of the school's curriculum to teach students about the natural processes involved as well as to introduce them to the benefits and environmental importance of green buildings.